I tried.
All right.
Might as well have all of the troublemakers in one class.
Okay. All right. Let's talk about these a little bit. We've got obviously the quiz on Monday. Now, I think those of you, well, when you got to, especially the later ones, on 56, I don't know how many of those you attempted. And then there were some of the papers I looked at, and a few answers down, but I'm not sure. I mean, some of them take a little bit of doing, and maybe you didn't run into some of the more difficult ones. But especially, there's some algebra that you're running into or should be running into, and then the derivatives. If we're doing L'Hopital's, we're going to do derivative top, derivative bottom on some of those, and some of that can get kind of interesting as well. And on the quiz, there's going to be kind of a whole mixture of those things. So we want to take a look at a few of those, but hope to have a fair amount of work time if we can, make productive use of that, where you can ask questions, you can work and get this, because you need to spend time on them, especially these limit ones. So let's just quickly talk through what the quiz will be about again. The slope field section 4.1 has about 4 things you need to be able to do. And I'd written those on the board earlier the other day. One is you got to be able to draw a slope field. Okay, so you're going to have to be able to draw a slope field. Like the one worksheet we had, you still have that worksheet, so you can go back and look at that. Where you just plot points and draw in the little slope segments and be able to draw a slope field. Okay, you need to be able to, number 2, do a matching. Of here's a slope field, here's some differential equations, be able to match those up. And you had a worksheet that did some of that, 2 worksheets actually that did that. You had a book assignment that did the matching. So if you've got questions about the matching, come see me, but there's going to be some of that. So I don't have any new assignments for you on those things, all right? And I guess the third thing there was the being able to draw a solution curve in the slope field. If I give you an initial condition for the difference equation, you can go in and follow the flow of the slope segments, and you can sketch the solution curve in there. So those 3 things with slope fields, we've had multiple assignments on that. Go back and review that, but I don't really have anything new to do on that, okay? Then the 4th thing that was in that section is the Newton's Law of Cooling problems. Be able to do the problems with Newton's Law of Cooling. And that's the part that'll be the calculated part, basically. I might let you use a calculator when you draw your slope fields, I suppose, because you have to calculate a little bit of the slopes, and not that they'll be that hard or anything. I just put that on that section. But mainly the calculator will be used just to do your solving of your Newton's Law of Cooling scenario. Now, I do have a worksheet here with some limit review problems, just some more practice limit problems, although we have plenty of those in the book that you can do as well. And then I do have a Newton's Law of Cooling problem on this worksheet, so that'll give you at least one more of those to practice. Okay, so that's the stuff that's from section 4.1. And then section 4.2 is basically these like what your book assignment is like here, which is these limit problems. And there'll be a whole, I don't know, 6, 8, 10 of those, whatever, something like that. Just a whole variety. Ones that don't exist, ones that do, ones where you want to use L'Hopital's rule, some where you might not need or want to use L'Hopital's rule, whatever. So you just need to practice a whole, variety of those for that. Okay? So probably our focus today will be on that, on the limit ones, and then I'll let you have some work time, and you can kind of see what you have questions on. Okay, so where do we start? What do you want to look at on the book assignment? Which one? 31. Okay, 31 is a good one to start with. So
We've got, all right, thanks. We've got a picture here. Here would be the picture, I think, for number 31. And all right, so for this particular one, you were asked to find the limit. Was it as x approaches 1? Was that what it said? Okay, so the limit. Well, it's when I switch to use the pin mode to whatever mouse mode, it makes that noise. So this is a limit as x approaches 1 of f of x over, what was it? X squared minus 1. So the first thing we do in any limit problem is what? Direct substitution, right? And that includes if it's infinity. We plug in infinity, which basically means we say what happens if you get really big x's? What is the output if you have really big x's? But here's 1 over 0. And f of 1, of course, is right there, which is 0. So we get 0 over 0. Okay, so 0 over 0, one of the things we can do is L'Hopital's rule. Another thing we can do is a factoring and canceling if we can, but with a graph, there's none of that we can do. So L'Hopital's rule is what we want to do, which says do the derivative of the top, so that'd be f prime of x, and do the derivative of the bottom, which would be 2x, and then plug it in again, right? Do the derivative of the top, do the derivative of the bottom, and plug it in again. So we plug a 1 in, and we get f prime of 1, and we plug a 1 in the bottom, and we get 2. Now, the people that I had helped on this problem, almost everybody, I think the reason was you didn't write anything down. I mean, you were looking at it, and then you were saying, okay, now do the derivative. You're doing all this stuff in your head. I don't know. I just think when you use the proper notation and you write stuff down, it kind of tells you what to do. Because now I got f prime of 1. Oh, yeah, that means the slope of f at 1. So I come in here at 1, and I want to do the slope of this graph. So I kind of draw a tangent line in here. It's really basically just a blue curve, actually. Looks like I go over 1 and up somewhere in here, I don't know, 1.5, 1.6 maybe. So it looks like I go up about 1.6 divided by 2, somewhere around 0.8. I mean, so it'd be an estimate. I mean, you'd have a little leeway here. I'd want to see your tangent line drawn in there if I gave you one like this. See about what you had. Oh, maybe, is that in the back? Is it not? 0.75. There you go. That's reasonably close. Okay? So, something like that. Okay, what else? 36. Okay, explain why L'Hopital's rule can be used to evaluate that first one, but not the second one. Well, I think it's because of direct substitution. I think if you plug in pi, right, in the first one, you get sine of pi, which is 0. And you plug pi in the bottom, you get 0. So that's 0 over 0. But on the second one, cosine of pi is -1. And so you get -1 over 0. So that's why you can't use L'Hopital's rule. Okay, you can only use L'Hopital's rule if you get 0 over 0 or infinity over infinity. And if you have to do L'Hopital's rule a second time, if you have to do the derivative, so you get 0 over 0 or infinity over infinity, you do the derivative of the top and the bottom, and you get 0 over 0 again, you have to re-plug. Every time you do that derivative again, you have to plug in again to see. I've already helped a couple people on problems where they plugged in, got 0 over 0, did L'Hopital's rule, and then did L'Hopital's rule again without even plugging in. I mean, right? You can't do L'Hopital's rule that second time unless you have 0 over 0 or infinity over infinity. So make sure you do that at each step along the way. Okay, what else?
Number 68.
68. Okay. Limit as x goes to infinity, and what's it say?
X squared times e to be negative x squared divided by 2.
Okay, which I would prefer to. You say it was x squared? Okay, so the first thing we do is direct substitution. Now I will say that sometimes it's easier to substitute numbers or infinity in if you simplify the rewritten problem a little bit. Okay, so that's something to keep in mind. It's one of the reasons when we were doing derivative on the gateway test that I wanted you to do some simplifying, because as we get into chapter 4, where we're actually using derivatives to do stuff, you know, we're going to have to work with those derivatives. So we need to be able to do the algebra and to simplify them and so forth. But anyway, so we go ahead and plug infinity. So a big number squared is going to be a really big number. Okay, and here's a big number squared is really big times a negative 1/2. It's going to be a really big negative. So what's e to a really big negative? That's a really small number, right? Because it's 1 over e to the, you know, whatever. So it's essentially 0. So what we have is infinity times 0. Now that's one of those things I told you about yesterday, but remember, L'Hopital's rule can only work with one of those two situations. This is the third indeterminate form, but remember what I told you, you need to do some sort of reciprocal thing with that. Now, what we talked about is 1 over 0 essentially means this, and 1 over infinity essentially means this. Now, I don't want you to confuse that with when we're doing limit problems. If you do a limit problem and you do direct substitution, and you get 1 over 0, you don't just write infinity, right? What do? You say does not exist. It's a vertical asymptote situation probably, and you're going to check the left and the right and see what's happening, right? So we make sure we understand that. But basically, the reason it's a vertical asymptote is because when you have 1 over 0, what you have is 1 over something really small, which is something really big. So what you have is an infinity situation. What we don't know is if it's positive or negative infinity, right? 1 over 0 is really saying 1 over something small. But what we don't know is it's something really small negative or really small positive, right? So that, we got to understand that. But in this problem, when we're talking about this reciprocal thing, that's so we can turn it into a L'Hopital's rule scenario. Well, what would be the obvious one to do reciprocal here? Yeah, the e, because it's got a negative power. So what I would do on this one is I would rewrite this, and this e can flip down here to the bottom as this. And so now we're doing this. Okay? Well, now as x gets really big, the top gets really big, and the bottom's also getting really big. So we have infinity over infinity. So we could use L'Hopital's rule. But is L'Hopital's rule even necessary? I would say this is one where I think you'd be doing more work than you should if you do L'Hopital's rule. What should the answer be on this one? Why 0? Exponential growth is going to outpace a power growth by a bunch. So the bottom is going to get bigger way faster than the top. And so this one is going to be 0. Okay? Now some of you who didn't have any work shown on a problem like this and maybe had that, maybe you did that in your head. Maybe you thought, oh, hey, I'll flip that to the bottom and exponential, the bottom is going to be way bigger. And that's possible. And on the quiz, actually, I don't care. I don't care if you show any work on it. Right? I think you should show the work that you need. Now, there are some problems where the work's very important, right? We talked about local max and min and number of lines, and you got to do this, got to do that, got to do that. Okay? But in this case, show whatever work you need to. But if you could just see that from there and could get 0, that's fine. But let's just say you tried L'Hopital's rule on this. Did anybody do that? Did anybody try doing derivatives and stuff? Okay? Sure. You get infinity over infinity, and so you start doing derivatives. So you do the derivative top, and that's that. And this is good because we need to practice on derivatives, right? And some of them, you can't just tell which one is bigger. So you have to do the derivative. So let's do it. So what's the derivative of that? So it's still e to the 1/2 x squared times derivative of that thing inside. It would just be x. Bring the 2 down in front. 2 times 1/2 is 1x to the first. So now we get that. Well, now you plug in again. Well, the top's still going to get really big. X is still going to go to infinity. The bottom's still getting really big. So this is still infinity over infinity. So what do? Do it again, right? You do it again. So you do the derivative of the top, which is 2. And now what do you have to do here? No. You have to do a power, not a power. You have to do a product rule, u prime v. This is a function times a function. So you have to do the derivative of the first thing, which we just got in saying is e to the 1/2 x squared times x, and then times the x left alone, right? Plus this left alone times the derivative of x, which is 1. So now we plug in again. So as x gets really big, this is going to get really big, plus really big. So the bottom is still really big, but the top is just 2. So 2 over a really big number is a really small number, 0. So L'Hopital's rule would have been a long way to do that one. It would have been nice to just know that, hey, the bottom's getting way bigger, way faster. This is what I mean by there'll be a variety of these problems that, and you'll have to think your way through what's going on.
Okay, some will be pretty easy, you know, there'll be probably some easy ones where you can just plug in, get something, there it is. And other ones where you have to do some of these things. Okay, somebody got another one? Here, this is. And then we're gonna do Goodbye. All right. All right, I'm sorry, what else? Somebody have another one? 72. Okay. 72 says ln of sine x, is that the one?
Yep.
Over x minus pi halves all squared. And the limit as x approaches pi halves. All right, now, on this one, we plug in pi halves, so sine of pi halves. So that's another thing you're probably going to want to be fairly familiar with are your sine, cosine graphs. You better be familiar with your natural log graph, okay, because this is all a no calculator thing. So if you've got to do ln and sine, cosine, you need to be familiar with these things. Okay, so if I plug pi halves into sine of pi halves is 1. What's ln of 1? 0. You got to know that. Okay, you got to know that. Now, you either know it because ln of 1, you're thinking e raised to what power would make 1, that's 0, or I prefer you make sure you know the natural log graph, and when you plug in a 1, you get 0. So ln of 1 is 0, and then pi halves minus pi halves is 0, 0 squared is 0. Okay, so you get 0, 0. So we could use L'Hopital's rule, and I would say that's probably a pretty good one, because it's hard to know about the relative growth rates of these things. We know that ln doesn't grow real fast, but remember, we're not talking about as x goes to infinity here, right? So that's a little different ballgame. We're talking about the bottoms getting small or the top and bottom both getting small, but at what rate? That's a little harder to see than some of those going to infinity kinds of problems. So L'Hopital's rule is probably the way to go. So the derivative of the top is what? 1 over sine times cosine. That's the top. The bottom, 2, leave the bottom alone, or excuse me, inside alone. And derivative inside just 1. Okay? So now we plug in again. So what's sine of pi halves? 1. Cosine of pi halves? Cosine of pi halves is 0. So 1 times 0 is 0. Put in pi halves here. Pi halves minus pi halves is 0. We do it again. So we need to go one more time. So now what do I got here? I got cosine over sine. Well, that's the same as cotangent, right? I think it'd be smarter to do that because I'm going to have to do the derivative of this. I'm not sure I want to do a product rule on that or cosine over sine do a quotient rule. That'd be kind of ugly. I think it'd be better to call the top cotangent. Okay, so what's the derivative of cotangent? Negative cosecant squared, right? Negative cosecant squared. All right, derivative of tangent is secant squared, derivative of cotangent is negative cosecant squared. Right, we've taken the gateway test, all passed it, right? Doesn't mean it's gone and behind you. It means you now know all those derivatives and will never make any mistakes when you have to do them, right? That's what that means. All right, so negative cosecant squared. And the derivative of the bottom. Now, people in the air class were getting confused on this. If I was doing this one, I would just distribute it. I mean, I just distribute the two. There's no power on there anymore, so just distribute it. Simplify it first. Now, what's the derivative? It's 2, right? The derivative of the bottom is just 2. Okay? Now, that works out pretty nice because cosecant, I don't like working with cosecant, so I'd rather simplify that into what? The reciprocal is sine, right? And since it's squared, it'd be the same thing. So I would say let's do the reciprocal of that. And so let's move that to the bottom as sine squared. Leave the negative up there. And now let's plug in our pi halves. So what's sine of pi halves? That was 1. Squared, 1 times 2. So our answer is negative. Again, just L'Hopital's rule. But I mean, what was the hard part of that? Well, the derivatives, right? I mean, the derivatives, being able to do the derivatives and do it properly. Remember those, and plug in and be able to do some stuff, right? But there it is. All right. Let me bring up one that came up in the other class that I thought was a good one to talk about. You may not have tried this. Some of you did, I know. Limit as x approaches 0 is number 59. I'll give you a second here to try this one. I'm not sure anybody had tried it. Maybe a few people when I came around had already done this one. If you did, just hold on a bit. But here's number 59. Go ahead and give that one a try. You can talk amongst yourself.
Oh, it's infinity. Infinity people. Wait, so I got one over zero. You have to do wait, so you do 1 over like 0, 0. Oh, 0, 0, 0, 0, 1. You just leave it as 1 over. And then you get a humongous number.
So it's a so you plug in like no, because this thing is usually like the cosine.
Wait, did I get some pictures? Here you go. And then you go turn it on.
What's the other one? Once I got into it, I got a little bit more.
All right, what do you got? Does not exist. I heard infinity.
Does not exist. 1 over 0.
Did you just put something in your mouth?
Something shiny.
That was a good.
Yeah.
You need to take some acting classes.
Now I heard some good stuff there. Does not exist. I heard infinity. Now let's talk about the calculator just a second, because over the weekend, if you were studying for this, the calculator can be a good way to check your answers. Right? Did I show you the limit thing on there? I mean, I think some of you already knew it was on there, but go on there, and you can not only do the limit as x approaches 0, but you can do infinity. You can do from the left and from the right. You can do both of those, all those things. But you do have to be a little careful with what the calculator tells you, because the answer that it gives you is not necessarily the same way I want to see it and so forth. For example, on this one, we've already said does not exist means you need to show more, right? Why doesn't it exist? In a one like this, as x approaches 0, you'd have to show from the left and the right. And so you have to do that. The calculator won't do it unless you ask it for that, right? You could ask it for the limit from the left and the limit from the right. So let's do that right now. So if you just type in this limit, just like that on your calculator. Now, limit is the same place where the derivative's at. In the template there, it's under the calculus in the menu. Okay? And then you can fill in the different boxes. And there's that little box in the superscript above the 0 where you could put a plus or a minus. You literally put a plus or a minus there. But for right now, just leave that blank and do x approaches 0. What's it say? It says infinity. Now, we said that should say does not exist, right? Now keep this in mind. Limit problems. If there is a limit, if it exists, it's a number. Infinity is not a number. So actually the calculator is telling you does not exist. It didn't give you a number. So when I get an answer, on a limit problem, I want it to be either a number, which is the limit, or it does not exist. Then when we tell more information about why it doesn't exist, one thing might be the limit on the left, limit on the right. Or it might be infinity or negative infinity, might be the additional information, okay, and so forth. Now, this told you infinity. Well, let's go through how we would do it, and then we'll come back to the calculator in a minute. So you guys all plugged in a 0, right? You got 0 over 0? Yep. So you did L'Hopital's rule, I assume, right? And you got, on top, you got cosine, 1 minus cosine. And now you plug in your 0 again, and this time you get 1 over 0. So now L'Hopital's rule doesn't work anymore, right? Now 1 over 0 tells you, hey, this limit does not exist. And it makes you think of infinity. We've talked about that, right? A number over 0 makes you think of vertical asymptotes, infinity, that kind of thing. So what we have to do is we have to check the limit from the left, and we have to check the limit from the right. Now go ahead and do that on your calculator. Go ahead and go up, arrow up, and grab that limit again. But this time, when you go in by the 0, then in the little superscript box, put a plus. And what's it tell you? Infinity. Okay, now go back in and redo it, and this time put in the name. It also says infinity. Now remember, when we've done that before, a lot of times we'll get infinity on one of the answers and negative infinity on the other one, right? Because a lot of time with an asymptote, you've got one going this way and one going down. But it's possible they're both going up. And that's what's happening here. But see, you're not going to have your calculator. So how are you going to show this? Well, you show it the same way we've always done it with plugging in. So we want to take a number just to the left of 0. And we want to plug it in. Well, what's a number just to the left of 0? Negative 0.001. Basically a small negative, right? So left of 0 is a really small negative. Right of 0 would be a really small positive. Okay? And we want to plug that in. Now this, it's harder to plug into cosine, a really small negative, than it is like x minus 3. What you need is a cosine graph. I think a good way to do it is a cosine graph. Now maybe you don't need the graph, but I think it's a good way to see it. So what's just left of 0 on the cosine graph? Well, it'd be right. It's just short of 1, right? So we're getting something just short of 1. Now on top, I don't really care that it's just short of 1. I'll call it 1. But on the bottom, I do. Because what we have is 1 minus something just short of 1. But small positive, right? So we'd have 1 minus something just short of 1, which is a small positive. So this is the thought process you would be going through without a calculator. And you'd say, oh, okay, 1 divided by a small positive is a big positive. And what about just to the right of 1? Or excuse me, just to the right of 0? Well, just to the right of 0, it's the same thing. It's just a little bit less than 1. So we get 1 over something just, well, again, 1 minus something a little less than 1 is a small positive. So 1 divided by a small positive is a big positive. So that's why it's infinity
both from the left and the right. And so what your calculator does is it goes ahead and just says infinity as its answer. If you ever did one on your calculator where on the left was infinity, on the right was negative infinity, then the calculator would say undefined, when it really should say does not exist. But that's what it would say, because they're not the same. But when they're both the same, it'll a lot of times just give you infinity as the answer. Okay? But I don't want your answer to just be infinity. Okay? I want your answer to be does not exist, and then I want you to give that extra information. Now, along those same lines, what if I gave you this problem, limit as x approaches infinity? Let's just do one where it's not x approaches 0, but it's x approaches infinity. Okay, I'll just give you two real simple ones here. So limit as x approaches infinity of 1 over x would be what? That's 0, right? A number, right? So we said a limit either is a number answer or it does not exist. And if it does not exist, you need to give a little more. So contrast that with this problem. Okay? This one, but what else? I want to see does not exist. I mean, that's part of it. It doesn't equal a number, right? It does not exist. And then what else could you put with it? Infinity. Or should you put with it? Infinity. Where as x gets really big, x squared is going to infinity. Now, if you think about it, remember, limits that go to infinity are horizontal asymptotes. Well, what's a graph going to do as you go way, way out to the right or way, way out to the left on the graph? It's got to do really one of two things. It's either got to come down and level off and approach some number, or it's just got to go up or down. I mean, can it do anything else as you go way out? Right? I mean, well, I take it back. Yeah, I could do something else, but everything else would be does not exist. I mean, it's either going to approach some number like this. Like, what is sine? What would be the limit as x approaches infinity of sine? It fluctuates from -1 to 1. What would you say for the answer on that? Does not exist. Is it approaching any number? Is sine approaching any number as you go way, way out? No, it's just bouncing back and forth from -1 to 1. I don't anticipate asking that one. But you would just say, does not exist. Why? It does not approach a number. So you would say, and then you could just write a little sentence. You could say, because sine just bounces back and forth from -1 to 1. Right? So if as you go way out to the right, the graph just goes to infinity, put infinity. If it goes down to negative infinity, put negative infinity. If it just bounces back and forth between some numbers, just put, that's what it does. Okay? Now, I don't know that you run into that, but those are the things that could happen. Those would be reasons why a limit does not exist, why it doesn't have a number that it's approaching, a number answer. Okay? And so how do I know about those? Because those are ones that people who worked on some extra problems here kind of went through. Those were some questions they asked. Those were some questions that they ran into. Give you guys a chance. Anybody else have another one? Something that you ran into? Trying to think of what else we talked about. Number 60. Okay, number 60. So we got tangent of 3x over ln 1 plus x. So we plug in a what? A 0 on this one? Now tangent, so you either remember that tangent is sine over cosine, and do that if you want. This is the tangent graph. That can be kind of useful in these problems. It has asymptotes here, and then it repeats itself. Kind of goes, and then just a whole bunch of branches. This is pi halves, negative pi halves, or you can use sine over cosine. It's kind of nice to use tangent though if you can. So you plug a 0, tangent of 0 is 0. ln of 1 is 0. We talked about that a minute ago. So that's 0 over 0, right? So do the derivative. What would that be? Secant squared. Take out a 3. Over, and then the derivative at the bottom. Times the derivative of it's inside, which would just be 1. Right? And then plug in again. What are we doing here? That's approaching 0. So we do 0. Now, secant squared is kind of hard to plug into. I'd rather do cosine, so I would write that as 1 over cosine squared, this top one. I think that's easier.
Okay, so if I plug a 0 into that, 3 times 0 is 0. What's cosine of 0? 1. 1 squared is 1. Under 1 is 1 times 3, so the whole top is 3. What about here? Put in a 0. 1 over 1 is 1. There we go. 1 over 1 is 3. That's nice. I mean, pretty basic. Derivative. You have to plug in first, get 0, 0. Got to do one derivative, and then give you a nice number. Okay. So we've covered a lot of the different scenarios. I mean, you get a number right away, or you get a number the second go round, or you got to check the highest power. Here you get 0, 0, then you get 1 over 0. So we've covered this situation where you have to check the left and the right. You know, that's it. I mean, that's a lot. Here we had 0, 0 twice, so we had to do the derivative 2 times before we actually got an answer. You know, here's one we talked about. We had 0 times infinity, so we had to kind of do a reciprocal thing. So we had to do the flip that one down, so we get that. So you do something like that. There was one. Well, what was that very first one in your homework? Is it x times cotangent? Was that on the homework? No, that was. Yeah, that was number 56. Nobody asked about that. Maybe that was an easy one. I would make that x over tangent, right? Do the reciprocal cotangent, make it tangent. And now you get 0 over 0, and now you can do a multiple of 0 from it. Okay? So that's kind of like that first one somebody asked. Make one other comment about number 64. Nobody'd ask about that one yet, but on that one you have to do the derivative of sine squared. What's the derivative of sine squared? And don't say cosine squared. What's the derivative of sine squared? 2 sine x times cosine of x, right? Because you've got to take sine of x all squared. So the derivative, you bring the 2 down in front, you leave the sine x alone to the first, times the derivative of the inside, which is cosine. Right? Make sure you, okay, do that. And then if you had to do the derivative again, what are you going to have to do? Product rule, right? You have 2 sine x times cosine x, so you would have to do a product. I don't know if you do on that one, but if you do, right, you have to do a product rule. So, you know, this stuff we learned in the gateway test and being able to do derivatives is very important. I mean, all of chapter 4 is stuff that involves derivatives. So somewhere along the line you got to do a derivative. On soul field stuff we didn't do too much with the derivatives, but certainly on everything else we do from here on out, it's a very big part of it. All right. Let's let me hand out the. Is that it? I mean, on homework questions anyway. Now, if you've got one, if you got another one, we certainly can. I'll ask it here as we work individually or with the group or whatever you want to do. We got 2 parts here to the homework. Well, one part, basically this worksheet, okay? But you can be working in the book problems if you want, right? Those 56 through 80, working through a bunch of those. Any of those would be good. I would stay away from 70, however. I think 70 you have to do like 4 derivatives and multiple product rules. It's a mess. So I'd stay away from that. Okay? But anyway, you can do some of those. Then this worksheet has another kind of mixture of some limit problems, and it has 1 Newton's law of cooling. Well, it's kind of a couple in one, but it give you a little more practice with Newton's law of cooling. And I've got the answer sheet to that up here. Okay, so you can compare and check that over. So that's the first thing, and that's the one that's related to the quiz. Second thing is this little teeny tiny packet. You almost call it a pamphlet. So
That's a huge fact.
now, this is the first of 4 of these. I'm sorry, did I not say that loud? This is the first of 4 of these packets that we will, I waited till after the drop deadline. This is the first, this is the first of 4 of these review packets for the midterm test. Now, these will be handed in, all 4 of these will be handed in when we take our midterms,
How many is it?
okay?
Yeah, how many of these are there for the final?
Oh my goodness.
8?
Ooh, large.
There would be, but, well, there'll be a number, but here's the thing. Here's the thing. What this is a full practice exam of the same number of questions as the entire AP test. Okay, so this sample exam is like a full AP test. Now, obviously, we don't know nearly enough yet to do all these questions. So what I've done is I've circled the ones that would be ones we need to be able to do for the midterm. So that cuts your work kind of in half right there. Okay? And we're not, and I'm not assigning the whole thing for Monday, just part of it. And actually, it's not really until Tuesday because you got the quiz Monday. So on Tuesday, we'll want to have this. But you'll want to get some of this done before Monday, I think, just because I'm going to give you another little bit to do Monday for Tuesday, right? So you want to kind of work steadily along. Now, they are going to seem more difficult here in the beginning, for sure. These AP test style questions, a big emphasis the rest of the year as we move along in new stuff will be to continue to go back and review and work on these kind of review questions and AP test style questions. As we go through the year, we'll get better and better and better at it, the more of them we see. Because they are a little different than what we've seen. In other words, they pull from all the different concepts that we've been learning. Okay? And you have to be able to recognize these kind of questions.
Will the worksheet be due on Tuesday like that?
Well, I'm not going to hand, the worksheet is yours to get ready for the quiz. Okay? I mean, that's your assignment for Monday, but I'm not going to check it or whatever. Just, that's yours to help you get ready for the quiz. These will, though, at the midterm be handed in, these packets, okay? Now, what you're doing for Monday are just the ones up to page 12. There's 4 sections, remember. There's 2 multiple choice sections, 1 calculator, 1 not, and 2 free response sections, 1 calculator, 1 not. Okay, the first section is multiple choice, no calculator. All right, I've circled, and it goes up to number 28 actually on page 13. That's the first section. Okay, is 1 through 28. I've circled the ones that you are to do, and I think there's about 18 of them. Okay, I think there's about 18 that are circled. All right, now, I want you to show any work that you need to do, or that should do. Now, there might be a problem or two where you can pretty much just tell what the answer is and not show work. On the actual AP test, and on our actual midterm, on the multiple choice, I don't care if you show any work. I just grade the answers, right or wrong. But on these review packets, I'm going to pick them up and I'm going to give a grade for them. I want you showing your work. I want you turning these in and just having answers in the answer box. Okay? Now, there might be a couple where there isn't really any work to show, and that's okay. But most of them, there'll be something to show. Because when I pick them up, what I'll do is I'll pick 1 or 2 questions that I won't tell you which ones they are. I'll just pick 1 or 2, and I will grade those more carefully. And then the rest of it will be kind of a completion grade. Okay? As I go through and just check that you've done. All right? And all 4 packets together will add up to basically a quiz grade. About a 30-point grade. Okay, so about 7 points per packet. The midterm is 2 parts, and each one is like a 30-point grade. So, like a quiz grade. So the midterm will be like 2 30-point quiz grades, and then the packets altogether will be like a 30-point grade. And the packets should be, the packet grade should really be 30 out of 30. I mean, really. I mean, we'll have some in-class time to work on. We'll go over, have time where I say, hey, any questions on the packet? We'll go over some. I mean, unless you're being extremely lazy, the packet grade should be a pretty good grade. Okay. So anyway, so for Tuesday, really, do those 18 circled problems up to number 25. Okay. And so the rest of the time is yours now to work on the worksheet, work on some problems in the book, practice these limit problems, get yourself ready for this quiz. If you feel really good about the limit problems and stuff and want to start working on a factor, that's fine. All right? Go to work. Again, I've got a couple of solution manuals up here for the book problems if you want to check them over, and I've got answers to the worksheet up here if you want to check those as you go along. Okay?
It's gonna be tough to find someone one day.